So today what we're going to talk about is we're going to first do a Rand simulation overview, as well as talk about the Ansys electronics portfolio. And then after that, we'll deep dive into our 5G. We'll be talking about 5G relative to PCBs, connectors, and antennas, as well as we'll touch a little bit on enclosure emissions and susceptibility. And then at the end, we'll tell you guys what's new in our Electronics Desktop 2024 update. And if we have time at the end, we'll do some questions. So for those of you who don't know Rand Simulation, who we are and what we do, our company is a company that specializes in helping other businesses identify problems within their designs, performance, and their products. We do this by meeting with you guys and discussing what your company does in the design process, and we help you identify the best way to use Ansys in order to simulate those designs to give you the best types of simulations. We also pride ourselves on being what we like to call partners with the businesses we work with, and we offer collaborative consulting as well as individual consulting. We aim to help our clients to innovate new designs and to optimize all their designs and ultimately benefit their business as a whole. So Ansys specializes in a lot of different areas, but like we mentioned today, we're going to be talking about electronics. We offer a wide range in our electronics portfolio, but today regarding 5G, we're going to be talking about 3 of our products. The main product that for those of you who are familiar with Ansys may know is HFSS. This is our 3D full field EM solver. This is going to be great because it offers multiple different solvers, including finite element method, i.e. your shooting bouncing rate, and hybrid. This is what you're going to use for all of your antennas, your RF microwave, and you can also use it for PCBs and such. It's very wide varying. We also have SI Wave, which is our specialized PCB tool, which is going to be useful for power integrity and signal integrity within IC packages and PCBs. Lastly, today we'll also talk a little bit about IcePack, which is the electronics thermal solver. This is going to be used for any simulations where you need to look at airflow, temperature, or any heat transferring within any electronics packages. So now we're going to dive into the challenges of PCBs at higher speeds. So a main one is that PCBs are becoming smaller while our data rates are increasing, and this is going to cause a lot of challenges within our PCBs. For example, we have to make sure that we're maintaining the signal integrity at the higher speeds. With these smaller PCBs, there are going to be high density interconnections, which require thinner traces to them, and this is going to degrade the signal integrity. Also, we're going to see EMI challenges happening on our boards at the higher speeds. A big concern with PCBs at these high speeds is going to be the thermal management. With data rates increasing, that means that there's going to be more power generated as well as more heat that's generated. This is going to directly apply to the material properties within our board and components, as these materials need to be able to manage the higher heats. One main concern is that the industry is talking about is the dielectric constants. Currently, the standard for the dielectric constants in PCBs is about 3.5 to 5.5. But with these higher speeds and higher heats, the industry is talking about lowering it to about 3. So that's something that we really need to pay attention to when designing and simulating our PCBs. Now, as we move on to the next slides, we're going to look at SI Wave and how we can use it to identify any risks in these challenges. So for signal integrity, SI Wave offers multiple different scanners and simulations that we can do to help identify any problems and to check our signal integrity. For example, we have our impedance scanner and our crosstalk scanner. Both of these are going to scan all of the single and differentially routed traces, and it's going to overlay a color map onto all of these traces so you get a great visual representation of what the impedance is at each point or what the crosstalk is at each point. What's really useful for this is that you can easily see where you might have problems with crosstalk or impedance and where you need to reevaluate your board. Within SI Wave, we can also look at the S parameters, such as insertion loss and return loss, and see if we're meeting the specific requirements that most boards have. We also can run a eye diagram analysis with an SI wave. This is going to give us our channel compliance. This is going to help us to determine the cause of data rate related failure like lost data packets or bit errors.
There's three key things that we can do within SI wave. One of them being the resident mode. This is going to allow us to visualize where we're at different frequencies, where we're having high voltages partake. Similarly, we can also look at the DCIR power as a map across our board to see where we're having high power in those areas, which may cause us to reevaluate for thermal or heat or even signal integrity reasons. Within the DCIR simulation, it also includes a voltage map similar to the power, which as well as the current vectors and magnitudes, which will let you see how the current is flowing through the board, as well as the via current density for each individual via. We also can look at the Z parameters in SI wave, which is going to be our frequency versus our impedance. This is going to be able to show you the resonances in the impedance spectrum, as well as you'll be able to look at the voltage ripple based on the current. So PCB thermal management, it was a big one that I talked about when discussing the challenges within PCB, because just to reiterate, 5G speeds are increasing. That also means that the heat is increasing. So being able to manage the thermal properties in your board is a major concern at these speeds. There's two main ways we can use IcePack, our thermal software tool. We can use it as a plugin to SI Wave, which you'll see on the left. This is going to give us a power overlay of the board and the components that we can see within SI Wave. We also can use IcePack as a standalone software. This is going to give you some more fidelity when looking into the thermal management. For example, what you're seeing in the picture on the other side is that we can actually see how the heat is dissipating through the air. This can be really helpful if you have multiple PCBs or components next to each other to see how they're going to affect one another. With that being said, we talked a lot about the different things we can do within SI Wave to look at PCBs. All of these are very useful for 5G and other speeds, but with 5G, it becomes more important that we are accurately simulating all of our PCBs to make sure that we are reaching good signals and we're not losing any of our data rates. Connectors are shrinking, but the standards are becoming higher. So how can we use simulation at these speeds? So at these high speeds and high frequencies, the RF transitions and the connector transitions are going to have a higher impact on the signal than at some of our lower frequencies. So it's very important that we're accurately modeling our connectors so we get an accurate signal when we're doing our simulation. What you're seeing on the screen is a model that I made for this presentation. It is a PCB board with two RF SMA connectors that start single-ended routed and become differential. One of the key things that's great about HFSS is that these RF SMA connectors I actually got from our 3D component library, which is a free library within HFSS where we can pull out different connectors or antennas and things of that sort to put onto our board. Similarly, you can also, if you're not designing the connectors yourself, but purchasing them from a vendor, you're still going to want to do the simulation, but you don't have the connector. What you can do is you can get an encrypted model from this connector vendor. What this is it's a hidden model of their connector to protect their intellectual property, but it's still going to allow you to fully simulate the connector as well as how it relates to on the board. So what are some of the things we can do within HFSS that's going to help us manage the signal integrity and these new standards that's coming at these higher speeds? Well, one main thing that's great about HFSS is our optimization tool. What this is it allows you to run a parametric setup, and it's going to let you put in a range of numbers that you want to run a specific variable for. For example, on our terminal S parameter plot 5, also an insertion loss plot, you can see multiple different results. What I did is I ran a scan of the dielectric constant from 3 to 5.5. What was great about this is I put my values in, let it run, and it did all the work for me. This is really useful because what this is showing us is what dielectric constant is going to push our roll-off farthest. Now, using this is not only limited to materials. We also can do scans like this for things like geometry placement, thickness, things of that sort. So what I also did is I ran a similar scan of the differential trace routing, changing the distance in between them, so I would be able to look at the impedance. So as we can see, we can once again look at our impedance graph shown below and see which impedance is going to be best suited for what we are looking for. Looking at S parameters is not the only thing that HFSS offers. We can also look at the electric field among many others and see how it's actually moving across our board. This is useful for seeing how the signal is moving through our traces in PCB, as well as helpful in identifying any areas that may be problem areas. We also can look at our single-ended crosstalk. For example, we are plotting the next and the effects of this model that I created. When looking at the RF board, I know we're going to want to look at the single-ended routing as well. So being able to look at the single-ended crosstalk as well as single-ended other S parameters is very important when looking at your connectors and making sure any routing across your boards is going to be correct. I'm going to go ahead and pass the mic to Matthias, and he's going to take you further into antennas. Thank you.
Hello, everybody. Thank you, Anna. My name is Matthias Lorick, and I lead our electromagnetics team here at Rand Sim. And so Anna talked a little bit more on the PCBs and connector side in the 5G realm. Today, I'm going to talk to y'all about 5G antennas and a little bit about enclosures, and then at the end, a little bit about for any Ansys users currently, what's new and the latest inside of the 2024 release. So when we're talking about 5G, you know, antennas is always something that is part of the system, right? Antennas are necessary to communicate wirelessly between devices. But what we want to designate first and foremost is that 5G kind of breaks down into a couple different categories. So there's 5G NR, or new radio, and that's going to be an operating frequency range that, you know, any antenna designers or anyone who's familiar with LTE or Bluetooth, Wi-Fi is in kind of a frequency range that they're relatively familiar with. Maybe they have the understanding and knowledge around those antennas. There's always new challenges that come up, but it's not particularly new when we're talking about connected devices, that frequency range. Now, when we get up into the millimeter wave frequencies at 24 to 40 gigahertz, there's a lot of additional considerations to take into play. Those antennas are often much more directional and advanced, and there's other considerations that, you know, such as heat and the ability to, you know, potentially beam steer the antenna. There's all additional challenges, but everyone could in the 5G space may fall into, you know, a different realm, but there are quite a few devices that will be in that 2 to 6 gig to satisfy that 5G NR. So what are some of the benefits of 5G's antennas? Well, the benefits, one of the biggest benefits of 5G is the increased data throughput for more users. So as we're starting to stream higher and higher amounts of data, higher resolution, that's going to come with a cost of higher data that needs to get delivered to these devices. And the way that we can do that is that we need to have antennas that work for that. So we often see very highly directional antennas that can reduce interference with other wireless devices. And we also have the ability to shrink down these devices, because at smaller or higher frequencies, it necessitates a smaller antenna typically. And so that allows us to reduce the form factor. This allows you to continue to enable and grow the Internet of Things or machine-to-machine communication industries, having a connected world, having devices be able to give us real-time feedback that we wouldn't have previously been able to do in the past. But with benefits, there also come with challenges. So radiation performance, receiver sensitivity, these are both requirements that your devices have to satisfy before they'll be allowed on to a carrier's network. They don't want a poor operating device allowed on their network because it gives them a bad name. The end user is going to, say Verizon or AT&T has bad coverage. No, it doesn't. It's probably this device. So that's why they have these requirements that you have to specify and meet. Other things to consider, a lot of these devices are very close to the body. So making sure that you're not transmitting excessive energy into the body and causing excessive tissue heating, such as evaluating for specific absorption rate or SAR. That's always a consideration when we have wireless devices. And while direct line of sight can really help with increasing the amount of data throughput, it can be a requirement as such. So multipath effects can degrade some of these, especially at millimeter wave signals or millimeter wave frequencies. It can degrade those signals. So sometimes the multipath is required. So being able to understand your environment and what you're about to deploy your device into can really help you understand and optimize that. And simulation can, of course, help shine light in those areas. So the first thing that I want to show you is just a simple antenna modeled inside of HFSS. And as a matter of fact, anyone who may haven't started, or anyone who out there who's maybe has an antenna design that's on the horizon for a product that they're developing, but they've never created an antenna before, or someone who wants to just kind of understand where to get started. HFSS comes built in with what's called an antenna toolkit. So if you can just specify, hey, I want to create a patch antenna, or I want to create a dipole antenna, or a conical antenna, or a horn antenna, there's a whole list of many different topologies where we just specify a frequency that we want it to operate at, and HFSS will script out and develop an entire model that we've shown here for us. It'll even create some of the necessary or most commonly used data reports, such as input impedance, gain, return loss, so that you already have a model ready to go that you can parameterize and modify as you wish. So for example, here we have a patch antenna that's operating just above 3.5 gigahertz. We have a gain of about 8.2 dB. And then here's a representation of our input impedance on the Smith chart. So the closer we have it to the center here, that's indicating that we have fewer amounts of reflections, more is radiating out of the patch antenna. So HFSS at its core can be very helpful to help you understand and design these antennas, whether it be you're just ideating the element of a greater array, or if you're trying to incorporate that into a device and understand how it performs and interacts with each other or other antennas nearby on that design. It is the foundation for helping you characterize and understand those things. So that brings me to the next category, or the next use case here, which is expanding that and now incorporating multiple antennas into the model. So instead of just having a single patch, we now have the form factor of a printed circuit board. And we have not one, but 3 antennas. We've got a cellular antenna, we've got a GPS antenna, and we've got a Bluetooth or Wi-Fi antenna. And each of those antennas are going to interact with each other, even though they don't necessarily operate at the same frequencies. So it's important for us to characterize and understand a couple different things here. So first and foremost, we want to make sure that each individual radiation pattern is sufficient to what we'd expect. So we want to make sure that the gain at varying frequencies is good enough, and that the incorporation of other things within our structure, whether that be antennas, batteries, enclosures, the actual PCB itself, the human body, if it's going to be placed up against the body, all of those things are going to impact the gain and radiation pattern of the antenna. So understanding how that's going to work truly inside of your system is very important. And like Anna mentioned before, We have connector models for within our library, but we also have a very large amount of antenna models. So there are off-the-shelf antennas that vendors have encrypted the design for that you can leverage inside of your solutions and implement inside of HFSS to understand how those performance increases, or how that performance is impacted by actually installing it on your board. Because one common gotcha, if you will, especially for people who are new designing these types of things, if they're using an off-the-shelf antenna, your ground plane, the dimensions of your board may be different than what they measured that on for their test board. And that can make a big difference on the radiation pattern in the game. So helping understand that, and then also seeing how the actual coupling between them is indicated. So some of these have, for example, the blue trace here is the GPS port, and it has a primary resonance right at 1575 megahertz where it's supposed to be, but it also has a little bit of a kind of a secondary resonance up around 2.4 gigahertz. So when we have a transmission of the Bluetooth at that point, we want to make sure that we're not coupling any noise back into the radio that could potentially get through. There's filtering that can be applied, but understanding how much the antennas couple within each other and actually looking at the S parameter coupling between them is another benefit, an important factor to consider when you're implementing multiple antennas inside of your system. So that's really all focusing on the antenna kind of in its, by itself. Of course, you could maybe put a little block of tissue next to it if there's, the human body, or we have a full complete human body model if you really need detailed fidelity. But ultimately, these devices will go somewhere. They're going to get installed either on a vehicle, or they might be on the move, or they might be deployed out in the fields, on buildings. So understanding how these antennas are able to propagate within their environment is also a common question and concern for customers, and it's something that simulation can help answer. So within the HFSS tool set, we have a solver that's called SBR+. It stands for Shooting and Bouncing Rays. And it is used to help visualize and calculate the propagation of antennas, whether they be installed onto a vehicle like an aircraft or a drone or an automobile, or understanding how they're installed in a larger environment like this city block that I've illustrated here. So we have two antennas. We've got one populated right in this upper corner, and then we've got one down here in the cross section of the street. And what will happen is it will leverage visual ray tracing to propagate rays that bounce through this environment. This is a 2-scale environment, and we have applied boundary conditions to the different structures and buildings that represent those specific materials. So we can calculate, if it's hitting glass, some will reflect, some will transmit. If it hits solid concrete, most of that's going to reflect off, but it will have some attenuation accounted for it. From that, we're able to see both, an S parameter coupling. So this would be like your link margin between them, from antenna 1 to antenna 2. But then also, if you want to kind of get an idea of a coverage scenario, you can also plot the field's response within that region and give an idea of what areas, so that in this instance, the antenna at the street is transmitting. You can kind of see how it propagates through the channels of the city blocks down the roads to help you visualize and understand how this performs in its environment. And so kind of this can fall into two different categories of people who would use it. The first one would be people who want to actually understand their antenna. They have it completely modeled up inside of HFSS. You can bring that directly into and link that as a source for these. But if maybe you're using an off-the-shelf antenna, but you're also trying and responsible with deploying this off-the-shelf solution, and you don't maybe necessarily have unique antenna information, we have a full library of antenna patterns depending on what type yours is most like that we can modify and adjust, so that you can even if you don't have any control of the antenna design, but you'd love to know if you deployed your devices, how they would perform, what's the best spot to put the gateway, things of that nature, you can still leverage SBR Plus to achieve those goals. All right, so back to our individual patch for a moment here. I kind of want to go through a little bit of a case study process and show off some of the more millimeter wave focused considerations inside of the 5G space for antennas. So when we talk about millimeter wave, a couple of common buzzwords would be, directional antennas, beam steering, multi-beam antennas, active steering. these things all kind of translate back down to that whole fundamental aspect of we want to push the maximum amount of data between the devices as we can. So if you think about a 5G millimeter wave base station, that's going to often be comprised of, some sort of an array antenna. And it's the benefit of an array is that if we recall from that initial image, the gain was, maybe 8 dB in its peak coming off the top, and it's relatively omnidirectional around the horizon. It's mostly just kind of a big blob. It's not very narrow and focused. So it's kind of radiating its energy more or less equally in a general direction away from the patch. Now, if we have a single user or a specific user that we really want to focus that energy towards, which is kind of what the fundamental goal of what 5G's, the directional beams are achieving, is you're basically trying to point it at the user at all times so that they're always getting the strongest signal to maximize that data throughput. To do that, we can take multiple instances of that antenna and place them in proximity to each other. And depending on how we apply an excitation stimulus to each of them, which breaks down to however, the magnitude and phase of the signal that we apply to each of these elements is going to be different and unique to each one. And by doing so, we are able to generate a much more directional beam with higher gain that also has the ability to be steered by applying the different phase shifts associated with it. So the process that we do that through within HFSS is we start with a single element. And this is always a good starting point. It allows you to optimize and make sure for the frequency that you are trying to design this antenna for is well designed for that single element by itself. Ultimately, you want to make sure that your patch is the right dimension for the frequencies that you're operating at. Or if you wanted to get more exotic with it, clip the corners or add an additional patch or have whatever your type is that's going to start with that single element, you create what's called a unit cell. And a unit cell is essentially the single element that then has, instead of traditionally applying a radiation boundary around the entirety of this model, we only apply it to the top and the bottom. So then on the left and right and front and back, the sides of it, we're applying what's called a lattice pair boundary, which allows us to then use the HFSS antenna array development tool to then specify a X by Y or an N by M customized matrix that we want, or N by M matrix that we desire. And from there, it will then create, using those applied boundaries, an equivalent model that allows us to take the solution solved from one and then propagate that with the associated boundary shifts to then recreate and give us the response of the entire array as we'd expect it. And then once we want to steer it, we can utilize our finite array beam angle calculator, where we specify a theta and phi angle, and then that would then auto propagate into our excitation sources. So this list here is all of our excitation sources for all of the different pins on each of these array elements. And by doing so, we can then sweep through those angles and see how the beam will steer and points towards the direction of interest. This is also helpful to understand the phase differences between these different elements for those beam steering calculations. And on the topic, while we're on the topic of beam steering is often achieved by individual beam steering ICs. So the ICs will take that signal and apply the associated magnitude and phase shift to each individual antenna element to achieve the beam and direction that we desire from an array. And so these components and any other RFICs and even the actual antenna and its losses that are incurred on the printed circuit board, all of these things can contribute heat to the system. And ultimately, chips are going to have a temperature rating that you can't exceed. There's going to be other things that can impact the temperature, like the environment. There's other reasons why you would want temperature to be low. You might have very sensitive sensors nearby that are temperature dependent. You might have other indications where it's already going into a very hot environment, so you really can't afford to have any more temperature rise than you already do. This is where Ansys IcePack can come into play to help you within the antenna space. So starting with our array model here, the array elements are all around the pattern here, and I've just drawn in 16 beam steering ICs, and they just have just a just an arbitrary 50 milliwatts of heat dissipation applied to them. And this antenna array is relatively small, so when we solve this inside of IcePack, we can actually see that the temperature is in excess of 100 C in this indication, which means that the board is absorbing a lot of this heat. The edges are okay, but right around these ICs, especially the middle ones, they're kind of maybe getting up into the excess of, they're definitely getting excess of your typical 85 C that you would want, for a maximum temperature rating of most common parts. So some sort of mitigation method is necessary. IcePack has a couple different toolkits that are built in. So whether you want to use forced air cooling, such as developing a fan, or if you want to use a toolkit here that I've shown to develop a heat sink, for example, that's what we did here. We just did a simple heat sink, the same size as the cross section of all these chips, made it aluminum or actually copper, but you can change it to be whatever material you want. And we can see that we've gotten a significant reduction in heat mitigated by implementing that. So it's pretty common to see heat sinks necessary on these types of arrays. So this is just definitely another way that you can, it's something to keep in mind, where heat is a concern when we're pushing, when we're doing beam steering, getting into millimeter wave space. So IcePack can really help unveil those problems before you've even developed and fabricated the system, so that you can make those problems known and address them before they become issues after you've already made it, where implementation can be a little bit trickier to execute. Okay, so that is a general coverage for 5G and antennas. But in the 5G space, 5G is kind of something that's everyone is going to have a little bit of a different application. Some things may be more relevant than others. But one area that is very common across not just 5G but the electronics industry in general is EMI. One particular issue, obviously there's stuff that can be done on the signal integrity side and the power integrity side to mitigate EMI issues that simulation with Ansys can clearly help you through. But also I wanted to shine some light on a couple areas where people may not be as familiar with, which is on the enclosure side. So within HFSS, we are able to bring in an enclosure, and from a couple of different methods. One of the ones that I like to use is just using that same antenna toolkit and creating kind of a simplified antenna model, or just sort of a noise source, if you will, that we place inside of that enclosure to help understand and visualize where within the enclosure we might be observing areas of potential EMI escape, if you will. A perfect metal enclosure usually will do a great job, but it's going to have gasketing, it's going to have slots, and especially as we go higher and higher in frequency, the smaller and smaller the wavelength will be, which means that smaller and smaller structures will be able to let EMI come out. An enclosure that you used 10 years ago for lower frequency shielding may not work as good as if you're moving into a higher frequency space of today and tomorrow. So here in this model, we just have a couple representations of different common things that you'll see on an enclosure, like conductive gasketing with spacing, copper fingers. We have an opening with no gasketing, so it's just a slight opening. We have slots and holes both present in this. This could be your model. It can give you just greater insights into what you're going to see when you actually have something transmitting inside of it, or if you're showering it with EM fields from an external stimulus. And so this slide really illustrates how HFSS is able to do this. And this is common and is applicable for any sort of HFSS simulation. This is what makes HFSS the gold standard in accuracy in the EM space for simulating these RF structures, is that we use an adaptive meshing process that reduces the input of the user, but still guarantees accuracy due to that process. So it will refine the mesh in the areas, as you can see, very, very refined in the areas where it needs it. And then it will simplify the mesh in areas where it can compute that and reach convergence to save time on RAM and simulation time, or to save on RAM and simulation time. And what it allows us to do is to visualize how those fields are propagating and escaping out of it. So from here, we can look at any sort of electromagnetic field, particularly of interest would be, the E fields, the J surface currents, H field. But from looking at it from multiple different views and planes, you can very well quickly pinpoint and specify and identify where within your enclosure the biggest amounts of problems are escaping from. So you can adjust the scale if you have a specific requirement that you're trying to hit. You want to have 20 dB of isolation from, or of attenuation from this enclosure. You can then adjust the fields to make that be very clearly seen. You are also able to animate everything inside of here, kind of like Anna had shown with her signal integrity RF connectors. So you can really see how these waves are escaping out of your model to address those EMI concerns. And it doesn't just stop there. We're focusing mostly on 5G, but if EMI is another concern that is common in your guys's design space, we have a whole other number suite of EMI specific test setups and applications that HFSS can help address as well. Things like radiated emissions, conducted emissions, susceptibility, bulk current injection, electrostatic discharge, etc. All right, and so the last thing that we wanted to go over with you all today. So for anyone who is an Ansys user currently of HFSS or SI Wave, this is particularly relevant to you. Anyone who may be interested in kind of learning a little bit more or dipping their toe into the RF realm or the signal integrity PCB realm with Ansys, this is just another way to highlight that Ansys is continually investing into their tools. Every year, we get about 2 new releases, and there's always great new functionality that comes out within them. So a couple things to note about here, particularly we'll start with HFSS, is that they have driven more development on the printed flexible circuits development. So being able to support parametric bends on printed circuit boards that have flex components with them, as well as applying mesh fusion to those flex PCBs as well. So anyone who's not familiar with mesh fusion has been developed over the last few years, which allows you to grab segments of a larger model and mesh them independently of each other. So it helps reduce the overall computational demand, allows you to solve oftentimes with less RAM requirements, and allows you to take a larger solution and break it down especially relevant when you have something where, for example, you have a enclosure with multiple printed circuit boards, or if you have a printed circuit board and then you have the modeling of inside the IC itself as well. You can utilize different regions or like layers, if you will, to then solve those individually, so that something that requires a really high fidelity, like inside of an IC or a section of a printed circuit board, can focus in that region and then let the rest of it be solved independently, and then HFSS will converge and stitch all of that together. So mesh fusion is a really nice beneficial process to help enable you in growing the scope of your simulation complexities. There's always continued improvements in the solver, so additional reduced RAM consumption, some additional array automation. Inside of SI Wave, we have a new electrothermal workflow for skin depth. We also now support components for the ice pack conduction simulations that Anna was showing, as well as some AC and DC blending for PSI and SYZ parameters. On the circuits realm, when we're talking about signal integrity, we've updated to have DDR5 details associated, as well as a semiconductor characterization tool. And then inside of HFSS 3D layout, we already had some encrypted models, but we now have built it off into having encrypted ICs as well as building additionally onto that rigid flex PCB workflow and enhancements. That's a very common area that we've seen. More and more boards in the industry are becoming a rigid flex type, whether that be from form factor or size constraints. So Ansys is continually making improvements and investments in that space on the electronics side as well. Okay. So if there was anything about this presentation that was particularly interesting to you that you would like to learn more, you can contact us at simulation@rand.com, or you can check out our website, randsim.com. We'd be happy to chat with you more about any of these areas in the 5G space, but otherwise, I wanted to thank you guys for your time today, and now we will move on to any available questions.
Alrighty, it looks like we have a couple here. So the first one is from Faisal. Beyond the basics, what unique signal integrity challenges are there in 5G PCBs? Can Ansys simulations predict crosstalk and losses at these frequencies?
Yes, they can. So beyond the basics, when we think about, the most basic thing that we would consider, I guess, inside of signal integrity would making sure that we're seeing acceptable transmission and minimal reflections between, two integrated circuits or 2 points that we're trying to evaluate. But taking that a step further and evaluating crosstalk both from the near end and far end are both things to consider as well. Ultimately, when it comes to 5G, really what we're thinking about is that when it comes to signal integrity is that it's just the higher amounts of data throughput and higher frequencies of operation that those data channels are working at. And that's not necessarily exclusive just to 5G. That's just in general, as data rates continue to increase and push those limits of, perhaps traditional design best practices that people are familiar with. That's where it's really important and critical to leverage simulation tools such as Ansys SI-Wave.
Alrighty, it looks like we have another one here from Jen. The webinar mentioned EMI shielding challenges. Can you elaborate on the specific shielding methods Ansys can analyze and simulate for 5G PCBs?
Yeah, so Ansys is able to simulate whether it be an enclosure, whether it be if it's a very detailed enclosure, we have other tools that can help address that as well. If it's an enclosure that we want to incorporate that has different mitigation methods within it, such as ferrite shielding, metallic shielding, other sorts of dielectric representations, we have the ability to change materials and recreate your model as accurately as possible so that it will give you insights into how its performance would indicate.
Perfect. All right. And again, if anybody here has any questions, feel free to send them over and then we'll address them here. If not, our contact information is up on the screen, so you can reach us at ransom.com, fill out the form, and we'll get a hold of you. I'll just give everybody a couple more seconds here to ask any questions before we wrap things up for today.